Thank you very much for the invitation. It's fantastic to be the first time in St. Petersburg. I want to talk about, as announced, Motivic Cohomology, group homology, and scissors congruences. So, in the sense of the title of the school, Motives and Related Structures, this series of talks is probably more on the side of related structures, or hopefully related structures. So, a rough outline of this series, I want to start with Motivic cohomology, so which may be more familiar to most of you, I suppose, than group homology or scissors congruences. So I'll not go into all the, very details, but I want to explain a bit what Motivic cohomology is, what we know about it, and what we still don't know about it, and why we would want to know. In particular, the sort of focus of this lecture series will be it's expected that Motivic cohomology for fields can be computed in terms of various complexes. So in the first part on Motivic cohomology, I want to explain how we would deduce the form of these complexes from conjectures about Motivic cohomology or about categories of motives. And then in the later parts of the lecture series, I want to explain how you can find complexes that roughly have this shape in group homology or also in scissors congruences. So, the last part of the series should then deal with sort of a different kind of geometry than we are usually doing here. Usually we do algebraic geometry. Scissors congruences is about the classification of polytopes in metric spaces, like classical Euclidean and non-Euclidean geometries. But for some reasons, one would expect that the structures that appear when you study sort of generalized versions of Hilbert's third problem, like how much information do you need to uniquely determine a polytope up to scissors congruence, that these structures are similar, related to things we see in Motivic cohomology. Yeah, so maybe the disclaimer, none of this is my own work, you would have known that. So this is the work has a long history. A lot of people have thought about things like this. For instance, to mention just some of them, Beilenson has a very deep conjectures concerning Motivic cohomology and what we would think is true in Motivic cohomology, and a lot of the work on Motivic cohomology has been inspired by conjectures of Beilenson. Then more recently, of course, Suslin and Woiwadzki have very much shaped how we think about Motivic cohomology now. And so the ideas linking these various fields like Motivic cohomology, group homology, and scissors congruences, there are a lot of ideas around this in the papers in the work of Goncharov. And maybe what I will also talk about. So, yeah, well. No. So this is the rough outline. I will talk about Motivic cohomology, so as a way to get the ideas what things should look like, and then I'll explain how things like this appear in group homology and scissors congruences. So this is not one of the lecture series where I say I'll start elementary and then it gets more complicated. Probably the first talk will be the most complicated one, and hopefully it will get a bit more elementary when I talk about group homology and scissors congruences, but I can only hope. Okay, so Motivic cohomology, so that would be the first part. So we should maybe start thinking about motivations. Why are we interested in Motivic cohomology, or what we want to do with it in the end? One of the reasons, one of the pieces of Bailensen's conjectural picture starts with motivation from algebraic topology and asks for a for an algebraic analog. Right, so one of the motivations is from algebraic topology. So what we have, you can look at cohomology theories for topological spaces. So we have cohomology theories for topological spaces. So this basically means we start with topological spaces and maybe put some restrictions and so on. And cohomology theory would then be a functor that goes, a contravariant functor that goes from topological spaces to, let's say, graded abelian groups. We've seen things like this in previous talks. And, well, examples of this are singular cohomology and topological K-theory. So we have singular cohomology. And we have complex K-theory. Right, which we can write down like K if we want. I mean, there are only two relevant groups. We can write it down like this. So we have, if the upper index is even, then we have homotopic classes of maps from topological space X to integers times BU. And if so this upper index is odd, then we have maps from X into the unitary group. So for singular cohomology, well, this is interesting. It tells you something about, this is standard motivation, holes in the space or whatever. And you can deduce various interesting statements about topological spaces when you know what the singular cohomology is. In complex K-theory, this is sort of hidden in what I've written here, is it classifies vector bundles up to stable equivalence, right? And of course, then there's not much need to justify why one would be interested in K-theory. There are so many problems, and I can't list one of them at this point, where you would want to know something about vector bundles on a manifold, or usually you're interested in manifolds. So this is definitely something that is interesting and links up so general algebraic topology in the sense of you study the homotopic category of spaces with actual geometry happening on manifolds. right? And well, of course, you have the general classification result now, vector bundles up to stable equivalence, but that only helps you if you actually can compute these groups. And you can do that. So I mean, for a singular cohomology, this is, well, fairly okay to compute, right? If you know something like a CW structure for the space, you can compute that. And if you have a smooth manifold, you can talk about Morse functions and all stuff to compute singular cohomology. So this is something that you can actually work with. And to compute K-theory, that may not be so easy, but what you can use is a Hitzepo spectral sequence. And that goes from the E2 term EPQ2. You take the pth cohomology of X with coefficients in pi q bu, and it converges to K p plus Q of X, where then, by Bott periodicity, we know that this is basically just it's the integers in the even degrees and the trivial in the odd degrees. So basically, on the E2 page, you would just have singular cohomology of your space, and then you have a couple of differentials and work all through the spectral sequence, but eventually you'll be able to say something about K-theory of the space. And this is one of the motivations why people started looking for Motivic cohomology. You want something that's an algebraic analog. So you want an algebraic analog of this whole situation. So on the algebraic side, well, and algebraically here means now we're not talking about topological spaces. We're talking about varieties, schemes, possibly smooth. So this is one of the side effects of working in A1 homotopy, that you usually think that all the schemes are smooth, and then you're surprised when people tell you that there are all these sorts of singularities that one can study. Okay, so yeah, frequently one reduces to smooth schemes to have nicer formulations or whatever. But a lot of statements can also be made for general varieties. So we are studying varieties, and the analog of K-theory was, well, basically developed in this form with higher indices as well. So I mean, you can define K0 if you just talk about vector bundles on the scheme and then divide out sort of additivity from exact sequences. But to define the higher K-theory, so that was done basically by Quillen. So, and that at least gives us an algebraic analog of the K-theory side. So we have algebraic K-theory. Of schemes. And how do you do this? Well, you can, this already appeared in Oliver's talk. So you can take a scheme and take the exact category of vector bundles you take a scheme X, and then you have the exact category of vector bundles over that scheme, and then you can apply Quillen's Q construction, and that gives you some space. And you can take its homotopic groups, and this is algebraic K-theory. Or, I mean, a different version, so you can also apply this Q construction to the exact category of coherent sheaves. Quasi-coherent sheaves. So this is much nicer behaved if we're talking about vector bundles, if the scheme is actually smooth. And this thing with the coherent sheaves, you can do in general, and then you get K theory, and then here with a coherent sheaves K prime or G theory, this sort of thing. So algebraically, this was done in the 70s, and this is this part of the picture here. And one of the motivations to look for Motivic cohomology was, of course, now you have K theory of schemes, and of course, again, you have this is linked to geometry, because it's studying geometric objects over schemes. And of course, such questions are interesting if you are in the appropriate part of algebraic geometry. The problem then is, how can we, so this category is usually very difficult to understand, and then it's not so easy to compute what the K groups are, even if you're just talking about K0, not even mentioning all this higher K theory, which is very difficult to actually work out. So you would also want to have a computational tool like this, and that was one of the motivations for starting to look for something that you might call Motivic cohomology. So what should be the analog? Of the Atiyah-Hirzebro spectral sequence. And I mean, there are various questions, namely, first, what should be the appropriate replacement for singular cohomology? And then you can ask, well, how would you set up the spectral sequence? So, as far as I understand, this was a question raised by П.Л.Чебышева. And so we arrive at one of the motivations for looking for definitions for Motivic cohomology, namely as an algebraic analog of singular cohomology of topological spaces. And of course, in this, if I'm trying to motivate this, the development of Motivic cohomology like this, then you don't just want to have a spectral sequence. Of course, if you have a spectral sequence, that might already tell you in special situations something. But yeah, you probably want to use the spectral sequence to do some computations. And so this not just means we don't just want to have an analog of singular cohomology, but we also want to be able to compute it in some cases. Okay. Right. So So by now, in particular thanks to the work of Voevodsky, we actually have answers to these questions. We have a reasonable definition of a Motivic cohomology that serves as a good algebraic analog or variant of a singular cohomology. And we also have a spectral sequence which depends on what kind of indexing you want to use. Minus q half or minus p minus q minus q here. The indexing doesn't actually matter, right? What I want to say at this point is really just that now we know that there exists a spectral sequence like this, established in some cases by Bloch, Lichtenbaum, and Friedlander and Suslin, which starts from, well, whatever Motivic cohomology is, I'll get to that point a bit later, and it converges to K theory. So in principle, you might use that to compute K theory, or to at least prove some things about K theory, if you know some things about Motivic cohomology. Okay, so in the days before all this sort of revolutions with the derived categories of motives, how could you possibly define Motivic cohomology? And this is what П.Л.Чебышева did originally. We know something more in the topological picture. right in the topological picture, maybe I should have written this over there. Well, no. I do it here. Topologically, the Atiyah-Hirzebue spectral sequence degenerates rationally. And that in particular tells you that K0 of x, so something about vector bundles on the space, so K0 of x tensored with the rational numbers is isomorphic to, I'm talking about finite dimensional things anyway, so I'm taking a plus here. So you can also, the K0 of x tensor Q, or finite dimensional CW complex or something like this, is isomorphic to the direct sum of all the even dimensional cohomology groups with rational coefficients. Right, so this is something in the case when you talk about rational coefficients, this is not so complicated. It degenerates, and then you really get this direct sum decomposition. And this is actually given by, you can write down the map here, it's going to be the Chern character. And so, if you don't have a definition of Motivic cohomology, you can just say, well, if it's supposed to satisfy all those things that we know from topology, then it should also satisfy something like we want to decompose the K groups rationally into those pieces, which should be Motivic cohomology. And this is, well, let me say it like this. In the times before we had a proper working definition of Motivic cohomology, this was sort of a replacement. You just take this rational degeneration of the topological Atiyah-Hirzebue spectral sequence and make this a definition of your Motivic cohomology. It should be things that you get out of a decomposition of K-theory tensor rationals. Right, so you take the higher K groups of scheme tensor with Q, and then, well, you have, just as in the topological case, you have Adams operations, and then you can make a filtration, and then say that that splits rationally, and so on. So what you get in the end is that so you can make this sort of a definition, and that was the sort of the definition that Beilinson worked with. So you take the K groups and decompose them according to the Adams operations that you have on K theory, and corresponding eigenspaces for the Adams operations will be then called Motivic cohomology groups. And so we mentioned this here. Beilinson used this as a definition. In the formulation of his conjectures and so on. And now we actually have an independent definition, which is a very, or various definitions that agree of Motivic cohomology, and you can actually prove that this statement holds. Maybe I want to say smooth here. Most of the time I'll probably want to work over a field. I'll mention some arithmetic issues, but yeah. Sorry? Sure.
In this isomorphism is also induced by Chern character?
Yes. That's the, I mean, so it's, this is most easily formulated if we're talking about K0. Right? Then you have Chern classes in this H2n, Qn, and I'll say in a minute that these will then actually be identified with Chow groups of X, and then this is really the Chern character. So, well, maybe I should say at this point, for K0, this was actually known before. And then the higher, for the higher K theory, this is basically used as a definition for Motivic cohomology. So, that's a bit of motivation. Why would you want to develop and study Motivic cohomology? There's another part of the motivation that comes from number theory. And well, when I prepared the lectures, I figured that discussing both these viewpoints in detail would be a lecture of double the size. So I will not actually say much about this. So what I'll say at this point is, well, you can attach L functions to schemes. And this is part of Bailinsen's big conjectural picture, that these L functions, or that special values of these L functions, should be understood in terms of Motivic cohomology via the Bailinsen regulator. And I guess I'll not really say much about this. I apologize, this is a serious omission, well, first of all, I'm not the competent person to properly talk about all of this, and it would take a lot of additional time. Okay, so, but I'll mention regulators and things like this from time to time at various places. So much for the motivation, why you want to define Motivic cohomology. And so the first preliminary definition sort of is already here, right? You want that Motivic cohomology, at least rationally, appears as eigenspaces for the Adams operations, or graded pieces of the gamma filtration on K groups, or however you want to say this. And so let me now come to another definition. And that's sort of also historically, I guess, one of the next steps. That's Bloch's higher Chern groups. Right, so this is some definition, of course, right? So what the drawback of this definition is that at this point, you would always only have a definition of Motivic cohomology with rational coefficients. And we know from algebraic topology that singular cohomology can be defined integrally. And Nikita already mentioned in his talk that it's very interesting to look at torsion from time to time. So what you would want to have is obviously a definition with integral coefficients. Bloch's higher Chow groups provides a definition that is with integral coefficients. So there you could have torsion. You don't have to ignore it, like in the definition here with the Adams eigenspaces. And in a sense also it's a more intrinsic definition because, well, of course you start with the scheme, but then already the step to a higher K theory goes away from the geometry, right? Well, you still talk about the exact category of vector bundles. But then talking about the homotopic groups of the Q construction is a significant step away from geometry. And then decomposing this according to Adams operations is even further away. And Bloch's higher Chow groups is really a definition intrinsic in terms of, well, the scheme. And as the name suggests, I mean, it's talking about algebraic cycles. We talk about subvarieties in the variety and relations they may satisfy, and so on. So you can do this for schemes over fields. And then, so one thing that needs to be defined to set up the theory is, well, most of the time I'll probably want to denote my field by f, because k is such a convenient counting index. So you can look at the algebraic n simplex, which is non-canonically isomorphic to an over the field. And this is really, I mean, it's the algebraic version of the topological simplex defined sort of by the same equation. Only in topology you would have this, that the coordinates have to be non-negative, but that's something that we can't say algebraically, and so we keep it just like that. Right, and then as usual in topology, you have the simplex, and then you have that faces of the simplex are again simplices. So you have inclusions of simplices as faces of other simplices. And the convenient way to say this is that you get a cosimplicial object, and the same thing is true here. You get all sorts of maps between these algebraic simplices which satisfy the appropriate identities you know from algebraic topology. And then you can look at the following thing here. Let me first talk about this. So we have X, the scheme over the field, and we can take over the product over the field with the n simplex here. So this, and this is very similar to what appeared in Nikita's talk already and in the definition of Chou groups. So this is the free abelian group generated by irreducible closed subvarieties in X times delta n of codimension P. Right, so this is the first step. This is not quite good enough. What you want to look at is rather the P of Xn. So this is the subgroup generated by those things. So those subvarieties which meet the faces properly. That means in the right dimension. Well, codimension, sorry. And meeting the faces, I mean, this is sort of like if you're writing down the algebraic 2 simplex, it's basically isomorphic to the affine plane. And in there, you have so the coordinate axis and this other line that goes through the points 1, 0, and 0, 1. And those would be the faces. Those would be 1 simplices. And
all this E will be one synthesis. All 3 lines will be.
yes, every one of those lines will be a one simplex. And yeah. And then you want that whatever subvariety you have, you can intersect with appropriate faces of the simplex, and then you should still have the right codimension. So you get this ZP of xn, and then you get a simplicial abelian group by basically intersecting with faces. So that starts like, let me put the star here. So we'll have an additional grading by codimension. And the last term is here, the n equals 0, and we have z star of x1, z star of x2, so those boundary maps are given by intersection with faces. And well, yeah, so it goes on like this. And as a special case, I mean, what you are talking about here, for instance, right, so we get a simplicial abelian group, and then the homotopic groups of this will be the higher choke groups. So we have ch star of x comma n. This is the these are the homotopic groups of the complex at the appropriate place. So I mean the ch star is the grading by codimension that you'll find here, and then the n tells you precisely which homotopic group you're looking at, so 0, 1, 2, and so on. And that's alternatively also the homology of the complex that you get by just taking the alternating sums of those boundary maps. Right, and what I wanted to say earlier, if you just look at what is happening at this point, so here you're talking about irreducible closed subvarieties in X, and here you're talking about irreducible closed subvarieties in X times non-canonically A1, and if you work out what the boundary maps are, basically intersecting with the faces 0 and 1, and that's going to give you exact, so the difference of these two things is going to give you exactly the rational equivalence, so that Cho star of x0, those are the ordinary Cho groups that already came up in Nikita's talk. And the other things with the with the positive n, they are then higher Cho groups. And then Bloch proved various properties for these things. And you've heard all the all of this before. So we have covariance for proper maps. It's contravariant for flat maps, or arbitrary maps between smooth schemes. You get localization sequences. Maybe first get Homotopic Variance, meaning that if you take, maybe should require smooth at this point maybe. So x times an mapping down to x induces an isomorphism. That's what's called Homotopic Variance. You get localization sequences, which in a situation when you have a scheme X, an open subscheme U, and its closed complement Z gives you a relation between the higher Chow groups of these three schemes. Maybe squeeze this in here. There's an intersection product like you would expect, and which is also very useful. You want to do, I mean, you want to study these things in particular also because you want to do intersection theory. And one of the more important points, maybe I still have it here, yes. There is actually a formula like this. So there are also Chern class operators for the higher Chow groups. And you get a formula like this, that the higher Chow groups actually appear. I mean, so that you get a formula that the Chern character induces an isomorphism between a rational K group and the direct sum of higher Chow groups. So I erased it just to write it again on the board. So with different notation. So we take P of x, q tensored with the rational numbers. This is going to be isomorphic to the p's graded part of the gamma filtration on the qth G group of x tends to q. Well, if x is smooth, I can just write k here. And then, well, yeah, in K theory, you have the gamma filtration coming from the Adams operations, and the pth graded part is going to be the pth higher Chow group with weight q. So you get a formula like you wanted. And yeah, so that's one possible definition of Motivic cohomology. Maybe because at some point I want to emphasize that also we want to be able to compute these things. This complex is not particularly well suited for computations. If you want to compute, like, even if you want to write this out, take X to be the spectrum of a finite field, which is not particularly large. So you're looking at the homotopic groups of the complex here, but the complex is made up of, well, here these things are generated by subvarieties. Here you just have irreducible closed subvarieties. You have the additional condition that they meet the faces properly. But because there is no bound on the degree, as soon as we're talking about n greater than 0, we're talking about subvarieties in affine space, and these things have unbounded degrees, and there's really a lot of them, even if we're just talking about a finite field and the which has only finitely many FQ points, but yeah, we don't have a bound on the degree. So even of a finite field, we're talking about complexes where the abelian groups are infinitely generated. So it's not particularly easy to do computations with this complex, which may be motivation to look for other complexes that might be able to compute Motivic cohomology. Okay, so the next step in history then is, well, this is, I guess you can say this is the modern definition. well, so you can define motivic homology via Voevodsky's motives or via the cycle complexes. You can look at the Red Book of Friedlander, Suslin, and Voevodsky. So this gives you alternative definitions. Well, Voevodsky actually proved that these more modern definitions using derived categories of motives actually agree with the definition in terms of Bloch's hierarchical groups. Okay, so this is only very, very short. So what I want to say at this point is that Voevodsky constructed categories dm well, and at this point, for this series, I will be mostly interested in the situation of so what is motivic cohomology over fields. So at this point, I can just restrict to fields, and there are definitions of such categories over a more general basis by Frédéric de Guise and Denis Charles Cieszynski. Well, other definitions by other people as well. Okay, so Voevodsky constructed these categories dm of f. Maybe we'll see a definition of the categories in the talks. Maybe, yeah. So let me just shortly say this is basically, you can look at presheaves with transfers, and then you want to enforce all sorts of computational rules. Namely, you want to have Nisnevich gluing, you want to have homotopy invariance, and you want that the motive Z1 is invertible for the tensor product. Right? And then you get these categories dm of f, and this is sort of, in a way, a replacement for the derived categories of sheaves with values in abelian groups in a topological space. So of course you would expect, if from this analogy, that you could define motivic cohomology by looking at suitable Hom spaces in this category. Maybe I should say that these are triangulated categories. And that's indeed the case. So maybe say. So Frédéric will probably say something more about these categories. Alternatively, you can also represent motivic cohomology in the stable homotopic category. And maybe Oliver is going to talk a bit more about this. So the actual formula, if we're talking about X smooth scheme over the field, is that we map from Hom X into Z Q P, some object in this category. And this is going to be exactly cho Q of X to Q minus P, or this suggests also a different cohomological notation. So if you shift by P, you should use a cohomological index P, and yeah, then you have these cycle complexes ZQ here. All right, so this is another way of defining motivic cohomology by means of Hom in these triangulated categories of motives constructed by Voevodsky. So what I should say at this point is so there's of course a whole world behind the just few words I've written on the blackboard. You have a stable motivic homotopy as an analog of the classical stable homotopy category, and you have dm of f as analogs of well, yeah, derived categories of abelian groups for topological spaces, or derived categories. And if you look over base schemes of sheaves with values in abelian groups, And so then you can transport a lot of the things people have done in algebraic topology to the algebraic world and use that to, well, first of all, give definitions of Motivic cohomology and prove many formal properties and so on. So one thing is you get the convenient framework to prove an algebraic version of the Atiyah-Hirzebruch spectral sequence relating K-theory and Motivic cohomology. It's a convenient framework to do all sorts of things that people have done in algebraic topology in an algebraic setting. So this framework also allows to reduce many questions about Motivic cohomology to fields. So we've done the definition for schemes here, but you see that from the definition in terms of higher Chow groups, right, if n is greater than 0, you're not just talking about a field, even if X is a field, right? You're talking about cycles in some affine spaces. So this is already very interesting if you're just looking at fields. And there are still open questions if you want to study the Motivic cohomology of fields. But this general framework here, talking about these derived categories of motifs, allows in quite a few cases to reduce statements for arbitrary schemes to the corresponding case for fields. So for instance, this is something that was the Benitz and Lichtenbaum conjecture. And then proved by Wojewódzki and Rost in the course of the work on the Bloccado conjecture. It's basically like, so what's the, the question is, we have a comparison. So we have Motivic cohomology of X with finite coefficients, Z mod L and weight N. And we want to compare this to the just étale cohomology of X with coefficients in mu L tensor N. And the claim is that this is an isomorphism if P is less or equal than N. So maybe X smooth here. Maybe not. And so one part of the proof structure of the Bloccado conjecture or Benitz and Lichtenbaum conjecture is that this statement for schemes can be reduced to the corresponding statement for fields. So whenever you have a statement for fields, then you get it for schemes. And then in the next induction step, even to prove it for fields, it's very convenient that you know it for some other Motivic cohomology groups for arbitrary schemes. So this framework provides a lot of very nice formal properties that tell you basically, well, once you have one statement about Motivic cohomology for some field, you can use the formal properties and this framework to get a lot of other statements about Motivic cohomology for schemes over that field or for other fields and so on. So in particular, after the Wojewódzki-Rost solution of the Bloccado conjecture, or proof, well, I guess we can say that we understand Motivic cohomology with finite coefficients, well, much better. Now, there's a lot of stuff that we can say about Motivic cohomology with finite coefficients, essentially because we can compare it to étale cohomology. and which is much, well, it's older. There are more computations for étale cohomology and so on. Right? So, so in a sense, yeah, we understand the finite coefficient situation much better. And many of the questions sort of that I'll discuss are dealing with rational coefficients. So for rational coefficients, depending on the questions we're asking, for rational coefficients, some of the things are much more complicated. And there are a lot of things we don't understand about the Motivic cohomology of in fields with rational coefficients. So let me list some things we know about Motivic cohomology. Well, one thing that we know, and which is a very powerful thing, is this, right? That for some indices with finite coefficients, we can compare Motivic cohomology with étale cohomology, and that helps a lot in understanding. So let me write again what I wrote here for this indexing. So if we're taking hi of x zj, so this is chj of x 2j minus I, and because of this we know some sort of vanishing. So this vanishes for trivial reasons, because there are no cycle complexes there. If this thing is negative, right? We had only definitions for non-negative things here. So, and if this is negative, this is basically the I greater than 2j case. And it also vanishes for trivial reasons, because again here these complexes were concentrated in non-negative degrees. So if the j is less than 0, then also the complexes there will just be zero there, right? So then there's a more involved vanishing statement, that is, if we are in the situation where I is greater than j plus the dimension of x. That does not directly follow from this, but it rather follows from this interpretation of Motivic cohomology as Homs in the category GM, or better, as we can also write this thing as hypercohomology of Motivic complexes, and then essentially it's the Misnevich cohomological dimension thing that implies this vanishing. So you see that different viewpoints give you different and interesting statements. So some other things that we know, I mentioned that already, is that of course the nth Chow group, so if we have the index 0 here, and with the other indexing, this is H2n x zn, these are the ordinary Chow groups. So if we're writing this down via Motivic complexes, we can actually identify the weight 1 complex, and that is the sheaf of units put in shifted by -1, which in particular implies that H1 of x z1 is going to be the global sections of the sheaf of units over x, and H2 of x z1, which is Chow 1 by this remark before, so that's the Picard group of x. And then we have Chow n of a field, comma n, this is isomorphic to Milnor K-theory. This would be due to Nestorenko Suslin, independently Totaro. Totaro actually writes down explicit cycles, giving you the elements in Milnor K-theory. And so because I'll be talking about weight 2, so in the interesting groups over fields. So H2 of F with Z2 coefficients is Milnor K2. This is one of the cases I already mentioned. And then H1 of F with Z2 coefficients is K3 indecomposable of F. We'll see this more later again. And that's the quotient of take Quillen K-theory of the field, and then you have a map from Milnor K-theory there, and you take the quotient. This is the indecomposable K3. Okay, so much for now. This is basically all I want to say about known computations. The next step would be, there are a lot of conjectures about Motivic cohomology, like Beilinson-Soulet vanishing, rigidity, or Beilinsen's conjectures also. And so I'll discuss these next time, and I'll discuss how, sort of, if all these conjectures were true, we would get alternative complexes which also compute Motivic cohomology. Let's say at least with rational coefficients, because the questions I'm interested in here mainly concern rational coefficients. So I'll discuss what these complexes would look like if we had all the conjectures, and then go on to we can find other complexes that look pretty much like this in group homology and scissors congruences. Okay, that's it for now.
I'd like to ask you one question, but for that, this blackboard so this block is something different about isomorphic means a conjecture proven by Vygotsky. Let's take X to be the spec of complex numbers. Yes, then we know the right hand side, yes, and then we know the left hand side.
Yeah.
And I think if we put this together with the spectral sequence, with the Ahia-Herzeberg spectral sequence, we compute K-theory with finite coefficients.
Yeah.
Okay, I think maybe one time later, maybe one should stay here. So
yeah, I think in this case it would actually be pretty similar. Yeah, I think you can also compare it actually to the topological statements about the homotopy of BU and so on. Yeah.
I just wanted to say that it's real, quite a computational tool even for complex numbers.
Yeah, that's true.
Other comments? Questions? Thank the speaker again.